Welcome back. So last part I have discussed the radio wave, the features of the radio waves. Now let me start with the next part, which is microwave, right? We have already discussed the radio waves. Now microwave. These are the uses, detection, everything we have discussed. Now for the microwave. Nowadays we are very much familiar with these things, right? Okay. First, wavelength. Okay, we should, I would not recommend to remind these things because this is not that much important, but we should keep in mind the order: radio, microwave, IR. If it will always good to remind these things, but if that is not possible, please remind this order. Okay, what is the wavelength? 0.3 meter to 10 to the power 4 meter. You should notice that as I go through this direction, the lambda is decreasing, right? For radio wave it is 10 to the power 4 to 0.1. Now it decreased to 0.3 to 10 to the power minus 4 meter. Okay, source. Source is different electronic gadgets, we can say. Also you can say that in Kilestone valve or magnetron valve, from these things also electromagnetic microwave produced. Okay, by which it is detected? Microwave basically detected by the point contacts diodes. Okay, and the uses. What are the uses? Microwave are basically used in radar. Also we know that microwave ovens, right? Ovens, micro ovens for cooking. Also to investigate the atomic and molecular properties. Okay, and one important thing, these micro ovens, the wavelength used in the microwave oven is 0.112 meter. Okay, so we can remind that. Let me state something here that in later you will study about some spectroscopy. By using spectroscopy we basically understand the structure of molecules, atom. So basically we can study inside the molecule or atom. So there are different kind of spectroscopic techniques for and for the spectroscopic techniques we need different region of the electromagnetic waves. Like radio wave is used in, I can write it here, for NMR spectroscopy. For NMR spectroscopy radio wave is used. Like that microwave is used in ESR or EPR spectroscopy. Okay, so these are the uses of, that's written here actually. So next is what is next? Radio, microwave, then IR. IR means infrared. Okay, so let me start again with, let me use the different color like this. What is the wavelength? Wavelength should be again decreased than microwave. So wavelength is 10 to the power 3 meter to 7 into 10 to the power 7 meter. One thing you need to mention that there is no sharp boundary actually, that if it is, let's say, if it is 0. It is 10 to the power minus 3 meter, if it is less than this, then it will be strictly, it will be our microwave, and here it should be our IR. Nothing like that. There is no strict separation. This separation made by us basically. There is no actually region in the electromagnetic waves. We made the regions of electromagnetic waves, the spectrum of electromagnetic waves, for our convenience actually. So there are some rough areas by which we actually classify the spectrum. There is no sharp edge detection like things that before this is this, or after this is infrared, nothing like that. There are some rough estimation, so we should keep in mind that always. So let's say this is the wavelength for infrared. Next is the source. What is the source? Molecules of matter at room temperature. Okay, means that in room temperature, let's say here, in every materials, everything that are constructed by lots of molecules, Avogadro numbers of molecules are there, we know that. So if we consider this pen, in pen also this is built by infinite number of molecules, right? So these molecules basically vibrates always. There are some motion, we know that each molecule there may be vibrational motion, translational motion, rotational motion. These motions are there. So if we consider the gas, then there will be all motions are there. If we consider liquid, then some motion are absent. In solid, we know that there is only vibration, because in solid there is no translational motion or the rotational motion. But in all cases, vibration is always there. So due to vibration of these molecules, what happens? Some electromagnetic waves are always emitted from any matter. Actually, as I mentioned before, that we can't sense, our biological eyes can't sense the infrared or other spectrum of electromagnetic waves except the visible region. That's why we can't see. We can't see the infrared spectrum emitting from the molecular vibration, but always due to molecular vibration, electromagnetic waves is emitting, and that's why there is some always that is the source, infrared electromagnetic wave. Okay, so that is the source. Okay, what is the detection by which we can detect? That is thermophiles bolometer or IR photographic film. That is the detection. Okay, so and the uses. That are used in IR photography. Several medical treatment, okay, and vibrational spectroscopy. It was ESR, before that NMR, IR used in vibrational spectroscopy, and it should be because as I said before, the source is due to the vibration of the molecules. To detect that vibration, we also use the IR spectroscopy. That's why there will be resonance. Otherwise, if we use the different spectrum, then there will be not exact resonance to detect the vibrational spectroscopy. To detect vibrational spectroscopy, we generally use the IR spectra. Okay, IR region. These are the uses. So next, we should move to the very important part, which is visible region. Okay. So this part we can actually sense by our biological eyes. Let's say we are this color is look like red, right? That because there is no color actually for any materials. There is no color. Color is totally actually understand by our eyes, our nervous system, brain. If our eyes receive any wavelength of electromagnetic radiation around 700 nanometer, then what happens? It gives a signal to our brain which stands for the red color. That's why we actually see this as red. That is the reason for different color of different materials. The color actually comes from the wavelength or the frequency of the electromagnetic radiation. Okay, for visible light it is 400 nanometer, actually 700 to 400 nanometer, or in meter unit we should write it 7 into 10 to the power minus 7 meter to 4 into 10 to the power minus 7 meter. Okay, so this is very very important. Okay, we will look into the in details the part of the, because we know that the visible light is VGO, right? Or right, VGO. So this red is around 700 nanometer and the visible region is violet is for 400 nanometer. In between this is different color. Okay, so we can say this green around 550, if I am not wrong, yes, 550 nanometers. So these are the different colors. So if there is electromagnetic waves of frequency, let's say wavelength, let's say 420 nanometer, essentially that will stand for the violet or purple like color. Okay, so these are the colors of visible light. After that, what is the source? So there are many sources for visible light, but this is we actually see those lights, visible lights, due to the transitions of the electrons in atom or molecule. Again, last time in IR case we said that due to vibration in the IR in the molecules, the infrared electromagnetic radiation actually emitted. But there are some electrons in any molecule or any matter. We know that there are electrons, electronic levels are there. We studied that HOMO, LUMO, etc., MOT, different kind of things, right? So what happens when these electronic transitions occur from one level to another level, that emitted energy actually remains in the region of the 700 nanometer to 400 nanometer, which essentially gives the light, visible light, or the color, we can say that. Okay, that is due to transition of electrons in atom or molecule. Okay, transition within the energy level. Let's say if there is two energy levels is there, this is ground level, this is excited level. If one electron excited from ground level to excited state, then what happens? It accept the energy from accept the photon, and if it de-excited, then it will emitted the photon, and this wavelength of the photon actually remains in the range of the visible light. Okay, that's why we can say that the materials by which this shirt is made, the electrons of these materials are making the transition which is around the 700 nanometer, which the energy gap of those transition between the energy levels, in which in between the energy levels the transition energy is around 700 nanometer, if we say in the wavelength scale. Then that's why what happens, it looks like red color, or you can say that this emits the, there are some different, I'm not getting that how the colors are produced, or we can see those colors. There are two types of spectroscopies are there, emission spectra or the absorption spectra. So that is quite different thing, but we can say that the transition between the electrons in these materials is surely around 700 nanometers, then only it looks like red. If it is around 400 nanometers, then it will be a violet colored t-shirt. Okay, so this is the source. Next, what is the detection? The eyes, photographic films, okay, and this visible light is used in electronic spectroscopy. Okay, so that's why we can see different color in different materials. That's due to totally due to the wavelength or the frequency of that electromagnetic radiation. If that essentially gives us the color, we can say that in very one line shot we can say that. Okay, so let me stop here in this part, invisible light. In next part I will discuss the rest of the region, the ultraviolet, X-ray and the gamma cosmic rays. Okay, so thank you.